Hyrum Anderson is going to be talking to you about your model.
Thank you, Hannah. Is that working for you? So, yeah. Today we're going to talk about your model. Your model's not that special, but this is more of a journey and a statement about models than about you. You are special. You are special, and in fact, your model might be special, but it's probably not your fancy model architecture that makes it so. And that literally is the punchline of my talk. And if you don't have time for anything else, this would be a good time to leave. But if you'd like to stay, the other points of my talk, I'm going to take you on a tour through deep learning, starting simple and going to complex, and showing how taking off-the-shelf concepts from deep learning in the image domain, how that might be applied, and we'll judge how successfully that can be applied for building malware machine learning models for Windows PE malware. And lastly, I will close with a few slides of my editorial comments about where I think you should be spending your real effort and time in building a machine learning model. So before I move on, I'd like to note that if you go right now to github.com in-game Inc., you are special. Then you will find code with Jupyter Notebooks where all of this is available to you. What you would need to provide for this are data, buckets full of malware and buckets full of benign data, and then you too can create from scratch your own machine learning model. So first, for context, a little bit about me. I have a very fancy PhD from the University of Washington, and the rest of these slides, the points here are supposed to convince you that I had a lot of experience in machine learning that apparently give me license to have my photograph taken with a wrinkled shirt and tasseled hair, as you see in this picture. And also to note that since my PhD work, a lot of smarter people have come along and mostly made it irrelevant and have made machine learning accessible to the barbaric masses and have otherwise reduced my confidence and my ego in having gone out for a PhD there. So with that, I'll want to tell you a story about how machine learning used to be in the old days. So first, there was data set curation, where there we go, where people would have to bring together data sets that were carefully curated. This would take an expert and lots of time. And step two, there was domain experts would have important meetings about what labels should be applied to which data samples and curate the data set. Domain experts would furthermore decide on how to describe those data elements. So if these were images, lots of papers about features like SIFT features that were supposedly useful for characterizing objects within images so that models could be built around them. And then model specification. So data scientists who spoke a lot of math would be able to talk about and propose various model types. And he'd throw words around like VC dimension and no free lunch theorem and other things that would make him sound smart that he would then apply to to his department, and they would believe him because these were big words. And out would come this model that was pretty good, that was pretty decent, and it was good for job security. But then deep learning came along with his rich daddy and his millennial skinny jeans, and deep learning changed a little bit the perception about what is achievable with machine learning. So in the new paradigm, and this is a little bit of a hoax, but in the new paradigm, one just simply downloads some data from the World Wide Web and then unleashes these images to Mechanical Turk and lets the masses label them, and immediately has a curated data set. A model is trained. You'll notice that steps 3 through 5 are replaced by deep learning, and then comes model validation. So, and all this, no more does the data scientist necessarily need to speak, math, but instead imports TensorFlow or Keras, and this has become extremely accessible to a lot of people, and that's a good thing. But what it's done is made me slightly less self-confident, more self-confident about my PhD, and given the millennials more time to tweet about how great their models are. So with that introduction, I would like to introduce to you, from ground zero, what we're going to do to develop a malware detection PE malware detection machine learning model. So if you were here earlier, there was a great talk by Lottie, raise your hand, who introduced this machine learning and its building blocks. I'm going to review in just 3 minutes some of those that are important for today's talk. So number one, and by the way, the notation will go like this. I'm going to draw a picture, and I'm going to give it a name and a little description, and one line of code in a platform called Keras that would allow you to instantiate that structure. So this is logistic regression. What it does is it takes some inputs, and from those inputs creates one number. And if you choose an activation function that squashes that one number between 0 and 1, this is called logistic regression. And that's just a building block that one can apply usually to the last layer of a neural net, so that one can create a model that says 1 means malicious and 0 means benign, and some number in between means right? So that is what logistic regression is for. Second are fully connected layers. And this is simply a transformation from an input, that could be the first input or some intermediate input, to a different representation using often a smaller number of numbers to represent the input. And that's achieved with this, again, dense. It's the same as logistic regression, except perhaps I might use a different activation function. A popular one is called a rectified linear unit, a ReLU here, which is on for things that are positive and just passes the input, and is off, passes a 0 for inputs that are negative. Lastly, for this talk, is a convolutional layer. And a convolutional layer is actually very much like a dense layer, except that it restricts, it has some local interest. So each output, like F right here, only takes as input his 3 most adjacent neighbors. And this size is called the kernel size. The kernel is actually the thing that's being learned. And the kernel is swept across the input and is applied consecutively to say those three, and the final 3 to produce outputs. And this comes from a long history of image processing, where convolutions are the key sort of atom that are used to extract edges and other things in image processing. And in convolutional neural networks, usually there's not just one filter, but many, many, many filters. So like there's 128 different little kernels that I'm learning that are 3 long that are represented in this output here. So that in Keras is a conv1d, where I specify a kernel size. These other, I will not refer to today, but I guess for the sake of completeness and because I wanted to prove to you that my PhD was worthwhile, I'm showing that recurrent neural networks and long short-term memory networks that are useful for keeping state, much like a computer would when learning from its input. So let's build our first model. And this model is called a multi-layer perceptron. And the building blocks that we're going to use are logistic regression for the output, the dense layers, and dense layers everywhere else. So in code, that turns out to be really just about 5 lines of code, maybe 16 with comments or something, right? Or we define a model in Keras. We have, we'll skip this for a moment, but we have added a dense layer, and then we've added an activation layer. These other elements of dropout and batch normalization are sometimes helpful, so that as Lottie mentioned in the previous talk, we don't overfit to the data. So for a fairly sophisticated model in 1, 2, 3, 4, 5, 6, 7, 8 lines of code, I have created a multi-layer perceptron. Now the thing about this multi-layer perceptron is that it's going to take an input and learn intermediate representations of the input that are useful for the task at hand. And the task we're giving it is decide whether the input belongs to the benign set or the malicious set of data that we provided it. And this might seem like magic, but by just applying simple calculus rules, one can define a loss function on the output and sort of assign blame for high losses all the way back at the input. And where the blame is high, those are the things we're gonna decide to twiddle and tinker with until the loss becomes low and the blame is relatively low for the input. So deep learning is all about minimizing the loss, which in turn propagates all the way back through something called backpropagation to the input, so that all of these edges, which define how to multiply and add things together, minimize the overall objective. So this is nice, but what's the input? So for our very first model, and there's code provided in the GitHub repository I've provided, we're going to define features. And I didn't spend a lot of time on this, but I'm going to show you it's actually pretty good. It's pretty good for a first cut model. So features are just a way to take the raw bytes of the PE file and condense it into, let's say, 2,500 different numbers that represent a malicious or benign file. And most of these have been published in previous works, and I've implemented them here in the code. But they are things like general file information. How big is the file? When is the compile time, right? Header file information, does the checksum check out for the PE file? Section info, what are the section names and section sizes? So in a PE file, there are different sections where data and code and resources and import address tables are contained. And we extract information about that in a part of a feature vector, imports information. So we literally query the PE file and ask what libraries are imported and which function APIs are used, and we include that in the feature vector. And if the PE file, if the executable has any exports, like a DLL would have. And then there's a second sort of class of features that don't require parsing the PE file, which I just slurp in the bytes, and I'll take a histogram of the bytes. So if things have lots of zeros in it, then there would be a spike there and might be indicative of some unused space or something. So a byte entropy histogram, that's courtesy of our friends at now Sophos, Josh Sachs and Konstantin Berlin, who kind of make this association between byte values and how they appear in complexity within your PE file. So if ASCII characters appear in sections of relatively low entropy, or if ASCII characters occur in sections of relatively high entropy. And lastly, I'm going to extract some strings. And this is really simple, like let me count the number of times I see a prefix that looks like a registry key. Or let me count the number of times I see C:\\, right? It's really simple string counting. And I'm going to throw all these together into a feature vector. Now you'll notice, the astute student will have noticed that some of these things, like section name, there can be very many of those. A section name can be almost anything that's 8 characters long. And because I want to have a small feature vector, we're using a common trick in machine learning called the hashing trick, which takes an input and maps it through a hash function, which tells you which bin in some, this notional 4-dimensional array, which bin I'm going to increment my count. So this is like a histogram, a noisy histogram of these input sections. So we've employed that trick all over, and that's common in scikit-learn and other things. So that was complicated. The point of this slide is that we're going to represent raw bytes as features so that we can build a multi-layer perceptron that inputs as its first layer this encapsulation of what does a PE file mean, and outputs a malicious or benign. And if we train this I think this was done on 100,000 samples, not a lot, but after you wait for about a half hour, then we get performance like this. What this means is that on a holdout set of data, if I take a new sample that this model has never seen before, and I extract its features and then pass it through my multi-layer perceptron, then threshold it at a threshold of 0.88, which was chosen to give me a 1% false positive rate, then I can detect 92% of all malware that's never been seen before. So that's pretty cool. That's pretty cool. And this is the confusion matrix. Now, this is where we have to level with ourselves. This is not a special model. This is not a special model. This model took just a few lines of code, multi-layer perceptron. This is kind of 1994 technology that we're applying here, except for some of the activation functions. So we want to make our model really special. And so let's begin our journey now in throwing away this not special architecture and diving into deep learning, what's been wildly successful for images and object detection and speech recognition and machine translation, and see if we can apply it to malware detection. Okay? So the point being, in all of those applications I described, those are end-to-end deep learning. There's no magical feature extraction. You put in an image, and out comes a cat. You put in an image, and out comes dog. But here, we had to go through this laborious step of extracting features. It feels like extra work. This is the old way of doing things. So let's see what happens when we try to, first, we're going to be more special now. The more special model we're going to choose now is a fully convolutional neural network. And all this means in the image domain is that I'm going to take, remember this kernel? I'm going to learn some filters to apply to my image that will be represented by this set of feature masks. And in turn, I learn some more filters on that feature mask to learn a different representation and so forth until this neural network has learned on its own choosing to minimize the overall objective features that are useful to tell apart dogs and cats and boats and birds. And at the end, I'll just plug in, guess what? My multi-layer perceptron. So all of this now becomes my feature extraction, and all of this is the code I showed you that's 5 lines long. So this is really cool for images because no longer does people have to write papers and papers about SIFT features, but they plug it in and they wait for a week and the model is trained, and then when they apply it to a new image, they can just give it the image and out comes a label. So the analog for this in malware, so in images, these are 2-dimensional structures and they have color. There's 3 fields, red, blue, and green. Malware is different, no color, 1-dimensional. So what we're going to do as our very first layer is do what's called an embedding layer. And essentially, for every byte in the malware, for every byte value, I'm going to let the deep learning architecture choose what color to make up for that byte. So instead of being R, G, and B, I could choose it to be 8-dimensional or 2-dimensional, and that's a parameter that I can tune. In our experiments, I chose 2, so we'll call it red and blue. And then from this sort of 1-dimensional color map that's a representation, so every byte in the PE file now has a color representation in this 1-dimensional image. And then I'll apply the same magic here, but 1-dimensional convolutions that just go in 1 dimension. And then tack on our multi-layer perceptron. Now that seems really cool. So now if I train this model and it works, no more PE file parsing. I give it bytes, and it gives me malicious or benign. That sounds really cool. It sounds really special. You can ask a question.
So how do you know, I know you said you don't have to label it, but how did the learning model figure out that was code in there?
Oh yeah, so that came from supervised learning. Yeah, so I gave it piles of data with images of dogs and cats and boats and birds. And the same is true here. I give it piles of data of raw bytes that were labeled malicious or benign. Yep. And I will refer you to the code and the Jupyter notebooks that will go through how that's done. Yeah, it's as simple as creating a directory called benign and putting a lot of Windows files in there or whatever, and creating a directory called malicious and then dumping virus share in there. Right? That's what you got to do. But as John Seymour would tell you, don't only put Windows files in your benign directory. Put lots of diverse style of benign. So we have a special model now. Let's see how our special model works. Our special model, so the picture is nice. In code, it's only about this long. And I've written the code in a way so that those with mere mortal GPUs can also run it. So instead of cramming the whole PE file into linear GPU memory, I've actually broken it up into little pieces. And you operate on the pieces independently, and that just helps with memory. And so that's what this time distributed is about. There's nothing temporal time about it. It's really just the pieces. So do my embedding layer over all the pieces of the malware. Do my convolution filter over all the pieces of the malware that I've broken up. And at the end of the day, I again add on my multi-layer perceptron. It's in fact it's called MLP for that, and then have get a 0 and a 1. And this would be really cool if it only worked. So, a ROC curve of 0.95. I've set a threshold of 0.81 to lock in less than 1% false positive rate. And we get about 50% of new malware samples. Well, clearly, this is not a very special model. And whereas the previous was maybe 1994, this is probably 2011. Let's get really special, really special. Let's go to 2014, 2015, and apply some really cool technology. So the reason you can't see this is because you and I would not really, it's hard to appreciate the scope of these models. This is called the Inception Model that's done by Google. And each of these, if you see each of these like structures here, I've blown up so you kind of see it. But if you were to give a slogan to the Inception Model, it would be, let's let the network decide what kernel size to use. And essentially, for every input, we give it choices. Want a 3x3 or a 5x5 or a 7x7. And let's do all those things and let the network decide which of those to use, or in fact, maybe blend them all together. And that's the theme of this Inception Model, and that's really cool. But as I was thinking about it, this is not really cool for, I'm not sure how applicable this is to malware, maybe it is. There's another model that's called Resnet. And it's actually slightly older than the Inception Model, but its sticker would be, let's let the network decide how deep to be. So everybody knows deep learning. Deeper is better. And in Resnet, the trick here is that you stack together these kind of structures, where I have these different weight layers, but then this shortcut. So if the network wants to, it can totally bypass this deep layer. Or if it wants to, it can use it. So the problem with deep learning, a challenge, is that the deeper you go, the harder it is to train. And so that what the Resnet authors did is they stacked together a bunch of these residual building blocks so that the deep learning could decide how many of them to include and how difficult to make its own learning task, which is kind of clever. And plus, we like Resnet because with a little craftiness, we can call it Malware Resnet. So for the first time today, I'm introducing Malware Resnet to the world, which is a very special model, and looks like this in code. First, we have defined a very fancy one-dimensional residual block in Keras, where we take, all this means here is we're adding together the pass-through, the input. Remember, that's the short circuit, and then this basic block. And I hope you'll ignore the fact that there's a comment out here because this breaks a current implementation of Keras that I'll fix later, I promise. But ignoring that, this is a simple pass-through block. And if I stack these together in a bunch of code that's even harder to read because sometimes special models take more code, then this is what you get. So I'll just note about this code is that you may, if you try to run this on your Mac, it probably won't run. So I've added a function to remove some of those layers on purpose so that maybe it will run in yours too if you have a mere mortal GPU. So here is a Malware Resnet, a very special model, and we'll see how it goes. And if you'll notice here with our very special model, I've chosen a threshold of 0.83 that it gets less than, in order to achieve less than 1% false positive rate. And now I can detect a whopping 9% of new malware samples. So I promise you, my talk was not to be about deep learning, but I did toy with these ideas for a very long time in frustration. And I'll tell you a couple things. I think there are ways to maybe get these to work with a lot more effort. But the point I'd like to make about this talk is that, number one, deep learning actually does require some significant work to get it to work right. We can't just take concepts from images and expect them to work well for malware. So images have this thing called image smoothness. So if you're a little miniature pixel marching along an image and you come to a sharp gradient, you've probably hit an object, right? If the brightness changes, that's indicative of something. But if you're a byte marching through a PE file, that looks a lot different. You know, a printable character in the header or in the import address table is much different than a printable character in the .text section where the code might reside. So for PE files, also, there's so much parsing domain knowledge that's left on the table if we don't use sort of those handcrafted features. So I guess the point here, and I'd love to chat with those who are interested. I have actually toyed in trying to use real deep learning and create a few gadgets that try to encode some of this domain knowledge. For example, if you believe entropy to be an important feature, then you can build an entropy gadget that's really good at calculating entropy or something like it, and it can use that automatically. So I have 30 seconds to wrap up in my commentary about what you could do better with your time to make your model special. And the hint is that it probably has nothing to do with your model architecture. That you can take that 1994 multi-layer perceptron with these features that I've provided for you, and you should spend your time in the data. And by that, I mean the biggest challenge in information security is the fact that the malware that the customer sees is different than the malware that you trained on. And the benign software that the customer uses is different than the benign software that you trained on. So paying careful attention to the labels of your benign-ware or your malicious samples, and I know a whole PhD dissertation about this very topic, can be really beneficial. Furthermore, just the prior distribution, so how much malware is on the network. This is the world that VirusTotal sees, for example, and this is the world that your customer network sees. Right? They're very, very different, and those need to be taken into account. At in-game, there have been times where our model release has been almost nothing except changing the data labels and changing the data that we've trained on. Okay, so this model was not very special, but it is pretty good. And in closing, I'd like to reiterate that you are special, even if your model is not. And I've named a repo for you called In-Game Inc. You Are Special. Your fancy deep learning malware classifier may work, but let's talk about how to do that later. And I hope that you'll come and see me at the in-game booth. All right, thank you. I think I've overstayed my welcome, and we'll take questions after. Is that right? Okay.